on the third day of our EXtremeClimTwin workshop for early stage researchers. Today with us is Dr. Carley Iles from CICERO, and Carley will help us understand more about attribution of extreme climate events. After the lecture, we'll have practicals. The practicals actually, the instructions for the practicals are in the shared folder, and also we managed to print a few of those copies for our early stage researchers who are here with us today. So without any further ado, please, Carley, the floor is yours.
All right. Hello, everyone. Thanks for coming. So, okay, I just try to share my screen. So, do you see my screen? And okay, I'll make it full screen. Oh, didn't work. Okay, yes, it did. Laser pointer. Okay, just a second. Okay, so yes, I'll be talking today about extreme event attribution. So just an idea of the schedule. So the lecture will take around 1.5 hours with 2 parts with a break in between. So the first part will be about what is extreme event attribution and the main kind of approaches. And then the second part will be kind of in more detail what the main steps involved in an attribution analysis is. And then we have a practical, so it will be about the 2007 heat wave in Serbia, and we will attribute it with Climate Explorer. And if we have time, there's also a second example, although I think probably we won't have time, but we'll see, which is flooding and heavy precipitation in the Danube and Elbe river basins in 2013. Okay, so let's talk about what is extreme event attribution. So it's looking at the causes of extreme weather and climate events. Specifically, in general, it's about the effect of climate change, the contribution of climate change to these events. So if we break it down a bit, so an extreme event can be something like a heat wave, cold waves, heavy rainfall, floods, droughts, hurricanes, snowstorms, and so on. And then attribution, I took the definition from the IPCC 1.5 report. So attribution is the process of evaluating the relative contributions of multiple causal factors to a change or event with a formal assessment and confidence. Oh, I can hear an echo. Okay. So in other words, attribution is to do with figuring out what the causal factors are and how much they contributed to the event. So in this case, what role did human-induced climate change play in a given extreme event? So after an extreme event, say there's a heat wave or there's a flood or a storm or something, often the question asked is, was this event caused by anthropogenic climate change? And that's a difficult question to answer, and generally in the past people have just said we cannot attribute whether a specific extreme event was caused by climate change, and in actual fact the question is not really a very good one, because if we're talking about a specific event, and a specific event is caused by a number of different factors interacting, climate change could be one of them, but at the same time we also get extreme events in a world without climate change. So it's not generally a binary answer of yes or no, this event was caused by climate change. So instead we can answer a different question. How did climate change affect the probability or magnitude of this kind of event? So the main difference is now we're looking at it in a probabilistic sense, and we're not just looking at this specific event, we're looking at similar events. So a similar event in the same location. And so we can answer this, and this is basically a field which is quite new. It's been around since about 15 years. And so nowadays we have the methods developed to answer this kind of question, whereas before we didn't. So another way of thinking about the whole concept is thinking about dice. So in the natural climate, the dice are not loaded. So you roll the dice and you'll get a 6, 1/6 of the time, if you roll them often enough. In the present day climate, it's like the dice are loaded. So you roll the dice and you end up with more 6s than you were expecting. So extreme event attribution is like asking, how does the probability of rolling a 6 change between the two climates with loaded dice and not loaded dice? So now if we go back to the climate, so this is a probability distribution function of a climate variable. Let's say it's summer mean temperature. So we have probability on this axis and temperature on this axis. So most summers are average, and you get a few hot summers and a few cold summers, and climate change can affect this distribution. So for example, it can shift the distribution to the right. So then you would have more hot weather and less cold weather, or the distribution could change shape. So in this case, it's got wider. So then you have more extreme weather of both hot and cold, or the curve could change shape. And so that would also have an effect on the extreme. So the way that this is changing depends on which variable you're looking at. So how did this extreme event attribution idea come about? Well, actually, it was proposed initially by a guy called Miles Allen at the University of Oxford. So he lives presumably quite near the Thames, and one year the Thames flooded and it was getting really close to his front door, which led him to ask himself the question of whether it would ever be possible to sue for climate change, like if it would ever be possible to claim compensation, I suppose, from the people who emit the greenhouse gases for the loss of value on the house for the fact that it now floods more often than it used to. So he proposed the way to do this would be to look at how the probability of this kind of event changes with climate change. So one way you could think about it is, if the probability of a flood increases tenfold due to greenhouse gases, then you could think that 9 out of 10 floods would be due to climate change, or we could attribute 90% of the damages to climate change. So the first study to actually put it into practice was the Stott et al. 2004. They looked at the 2003 Paris heatwave, which was a heat wave which caused about 70,000 deaths. And they found that this heat wave had at least doubled in likelihood due to human influence. And since then, there's been a lot more studies. So, for example, some of them are published in this BAMS supplement. So since 2011, there have been these supplements every year looking at the extreme events of the previous year. So the first one was in 2011, and there were 6 studies, and more recent editions have more like 20 to 30 case studies. So this is just a map. You can find it on Carbon Brief. It's showing basically, I think, all the event attribution studies that have been published to date. So I just wanted to show that the geographical coverage is a bit uneven. So you have a lot of studies in the US and in Europe and Southeast Asia and Australasia, but then missing studies in South America and Africa and over here. And yeah, well, up here too, I guess. Oh yeah, this was something I added in at the last minute. So these 2 people, Freddie Otter and Gert-Jan van Oldenburg, they have been very, they've really pushed forward the field. They've contributed a lot towards extreme event attribution science, and they were actually listed in the Time list of the 100 most influential people of 2021 for their work in extreme event attribution. So it's just to say that this is useful stuff, I guess. Okay, so how do we do it in practice? So we're looking at how has the probability of a given class of events changed between the world as it is now, which is often called the factual or the actual world in extreme event attribution literature, compared to the world that might have been if we had not released lots of greenhouse gases. So that would be called the counterfactual. And the simplest approach is basically to simulate the world as it is now and the world that might have been with climate models and count the number of events. So for example, a heat wave in a given region over a certain temperature threshold, say 35 degrees or something like that. So in reality, you need to run these two different worlds lots of times in order to get enough statistics. So you have a large ensemble of both. And then this is just my visual representation of, so each dot is supposed to be a heat wave over your temperature threshold that you're interested in. So in the factual world, the world as it is now, maybe you have this many events, and in the counterfactual you have fewer events, and you can use that to make a probability ratio. So here's the probability ratio, and this is the main number that comes out of an event attribution study. So you calculate it, it's just the probability of the event in the factual world divided by the probability in the counterfactual. Sometimes this is called a risk ratio. You might see that sometimes. So for example, if nowadays the event was a 1 in 5 year event, and it used to be a 1 in 10 year event, or it would have been, then the probability ratio is 2, which means it's twice as likely now as it would have been. I mean, maybe this is not a particularly extreme event if it's happening one in 5 years, but it's just for an illustrative example. You will also see results expressed as fraction of attributable risk. So this is the probability in the present day minus the probability in the world that might have been divided by the probability in the present day. And in this case, the answer is 0.5. So you could think of it as if half of the risk of this kind of event is due to climate change. So here's an example. This is the Russian heat wave that occurred in 2010. So this is a map of what it looked like. So if I remember correctly, this map is for July, and it's comparing with an average July. So this particular July was 6 or more degrees hotter than average, and this heat wave was associated with 55,000 deaths, a reduction in crop production of 25%, and 15 billion US dollars losses. And so you can run climate model simulations of your two climates. So in this case, there's the current climate, which is the 2000s, and the earlier climate, they just used an earlier period, which is the 60s. And so basically you simulate these periods lots of times in an ensemble of climate model simulations, and then you can plot the results. So if I just try and explain what this graph is showing, so we have temperature on this axis and then return period on the x-axis. So return period is, well, say it's 100, that means that it's a 1 in 100 year event. So it happens on average once every 100 years. And you can also think in probabilities. So probability is also plotted on the x-axis at the top. And then all these circles, they are Julys from the different model simulations. So yeah, each circle is a July, and you can see that this line is above this line. So this line is the current climate, and the blue line is the earlier climate. So this red line, the current climate, is warmer than the previous climate, and you can use it to read across. So if the heat wave was 24 degrees, which doesn't sound that hot, but it's just because we're averaging it over a kind of large area and a long time period that makes it the temperature less than it would be otherwise. So, but anyway, so if it's like 24.5 degrees, so we can read across and then read down. And so we find that it's a 1 in 40 year event, more or less. And in the previous climate, we read down over here, it's a 1 in 100 year event. So the probability is actually increased by about 2.5. I forgot to say before, sorry, that the return time can be calculated as 1 divided by the probability. Or you can also work it out as the sample size divided by the rank. So yes, okay, so the probability has increased by 2.5. And then, but you can also look at it in terms of magnitude. So for that, we would need to look in a vertical direction. So for a given return period, so 1 in 40 year events, we see that this red curve is about 1 degree hotter than the blue curve, which means that this event was 1 degree hotter than it would have been in the past. And we can also compare that to how big the heat wave anomaly was compared to an average July. So that's the averages shown down here, and you can see what proportion of this arrow, the red arrow, is compared to the grey arrow. And you see that it's maybe, it counts for 1/5 of the heat wave magnitude. So that's another way of looking at it. And actually this heat wave, there were 2 publications on this heat wave where the results seem quite contradictory. One found a small increase in magnitude, and the other found a large increase in the frequency. And initially that looks contradictory, but actually it's not. It's just 2 different ways of looking at the event. The small increase in magnitude, large increase in probability. So the framing is important. So the framing is whether you're looking at the magnitude or the probability, it's just important to be clear when you write up the results which you're looking at to avoid confusion and apparently contradictory results. Okay, and there are some different flavors of extreme event attribution. So I'll try to explain that on this slide. So there's unconditional, conditional, and also the storyline approach. So unconditional takes into account everything, and it gives an overall probability of the overall probability change of this event happening. The conditional, it kind of well, you can hold one or more aspect constant, so you can kind of like divide the part of it, the causes of the event, and just look at some parts. So for example, you might be interested only in events that happened with the same atmospheric circulation state as the real event had. So for example, for a heat wave, that could be a blocking pattern, or you might be interested in events with the same sea surface temperature pattern, or that happened with the same phase of the El Nino southern oscillation as your real event did. And doing this can help disentangle the causes of the change in events. So often it's split into thermodynamic versus dynamic. So thermodynamic is stuff to do that's more directly related to heat, like temperature. It could also be precipitation changes. If you have more moisture in the air, then you can have more rain. That's also a thermodynamic change. And dynamic is more to do with the atmospheric circulation. And so the thermodynamic changes are generally more certain. They're simulated. Like climate models agree on them. We understand why they should happen. Whereas dynamic is less certain, partly because climate models don't agree about how dynamic changes should change under climate change. And also the forced signal is very small compared to the variability, and there's less understanding of how atmospheric dynamics should respond to warming. So yeah, doing this conditional analysis helps you to disentangle these things by holding the dynamics constant, for example, which allows you to see more clearly what the thermodynamic component of the change is. But you only get a conditional probability at the end. So it doesn't tell you what the overall probability of, for example, a heat wave is. or how that changes. It just tells you that your heat wave changes given a certain atmospheric circulation state, for example. And then the storyline approach is kind of, it overlaps with the conditional approach, but maybe it's more of an extreme version. So here we're not trying to work out the overall probability of the event changing. Instead, we're trying to pick apart the event and look at the role of climate change on some of the causal factors. So for example, for a hurricane, this could look at looking at the increased water vapor holding capacity of the air and its effect on precipitation. So that would be a thermodynamic change, or it could be looking at the effect of warmer sea surface temperatures that have warmed due to climate change on the hurricane strength and precipitation amounts, because the warm SSTs is what causes, what fuels the hurricane. Or you could look at the sea level rise part and what effect that has on the storm surge. So as an example, I found that, well, I found this in a paper somewhere, that Superstorm Sandy in 2012, there was some, so the sea surface temperatures were 1 to 1.5 degrees warmer than average in that area. And there was a study where basically there were some weather forecasts, and they also tried running them without the sea surface temperature anomaly. So they put average sea surface temperatures instead. And they found that this warmer sea surface temperatures caused the depth of the storm to increase by 7.6 hectopascals. The wind speeds were increased by 3.6 meters per second, and the precipitation increased by 35% just because of the warmer sea surface temperatures. So that can help us also to understand what the effect of warming, like global warming on sea surface temperatures, what effect that could have on hurricanes. Actually, I'm not sure if this was a hurricane or not, but more or less. For a drought, the storyline approach could be looking at some components like the effect of the warmer temperatures on evaporation, or the effect of precipitation changes on the drought. But yeah, as I said before, that atmospheric circulation changes are generally less certain than some of the other components. And yes, it overlaps with the conditional attribution and doesn't aim to give an overall change in probability of the event. Okay, so then some methods. So the first method I came across for this was the weather at home approach, which I find actually quite an understandable approach. So basically it involves running model simulations of the year that you're interested in, with and without anthropogenic forcing. It's actually run on volunteer computers in order to get really big sample sizes, and then you can look at how often your event happens in the two different sets of simulations. So it uses a atmosphere only climate model, and sometimes it's downscaled with a regional model. And it uses observed sea surface temperatures. So you prescribe them into the model, and then it runs the kind of atmosphere part with information from the sea surface temperatures which really happened. I mean, for the counterfactual world, you then have to subtract the global warming signature of the sea surface temperatures, because otherwise your sea surface temperatures will be too warm. You also have to obviously have pre-industrial greenhouse gases as well. So this is just to illustrate some sea surface temperature warming patterns. So this is the one for HADGEM 2 ES, and here's the same for IPSL model. And you can see that the warming signature in sea surface temperatures is actually stronger in this model than in this model. So there's some uncertainty about what the global warming signal in sea surface temperatures actually is. So they overcome that by running simulations with multiple different sea surface temperature patterns subtracted. And so what's this? Okay, and so you end up with the result something like this. So this is looking at 4-day average precipitation in the Elbe catchment. So that's actually what the second practical is about, but it's using, we use different model simulations than what they used here. And this is actually an example where there's not a clear result. So we have in red, this is the climate model simulations with all forcing, so it's the present day world, and then the blue is the counterfactual world, the world that might have been. And the reason there's a big kind of spread horizontally is because of these different sea surface temperature patterns. And then the dark blue is combining all the light blue estimates, but you'll see that there's not a huge difference between the two lines. So I think the study actually concluded that it was inconclusive, or that there was no obvious impact of global warming on precipitation in this river catchment. But that previous example I showed you, the Russian heat wave, or this one, this was also done with the weather at home approach, and here we do have a clear answer. So this weather at home approach is actually a kind of conditional event attribution, because you are prescribing the sea surface temperatures. So the sea surface temperature pattern is like what actually happened during your event. So it gives you a conditional probability. You can also use CMIP5 or CMIP6 to do this kind of event attribution. So we talked about those in the last workshop. So you can do this by comparing simulations with just natural forcing, so that's volcanoes and solar variability, or you can use the pre-industrial control simulations compared with the all forcing simulations. So those have all forcings like greenhouse gases, anthropogenic aerosols, as well as the volcanoes and so on, solar. So generally the ensembles are a bit smaller. If you're looking at CMIP5 or CMIP6, maybe you have 100 members per world, whereas before with weather at home there were more like 1,000. So your sample size is smaller, but you can get around that by taking a time slice around the date of interest. So I tried to draw this to give a visual representation of what I mean. So this is time series from 1900 to present, and the green is the natural simulation, so they don't really have a trend, and then red is the all forcing simulation, so they do have a trend. So say this is for TXX, that's the maximum temperature of the year, and then you can take a time slice around the event you're interested in, like this for example, and you can use these years to make a probability distribution function. And so we have these probability distribution functions here. So you can see that the red one is shifted warmer than the green one, and you can use this to work out how the probability of your event has changed between the two ensembles. So it's also possible to do some analysis using observations. It's harder to kind of disentangle with observations what is caused by global warming and what's caused by something else. And also you tend to have the natural variability tends to confuse the results a bit more, because you can't run multiple ensembles of the real world, there's just one. But you can, the way you do this is say this is a time series of annual maximum temperature in De Bilt in the Netherlands. So you can see that there's an upward trend, but to look at the probabilities, you have to fit a distribution, and then you can look at the return period, and so you use a generalized extreme value distribution. So I'm going to talk about this in more detail in the second half, but this distribution, because there's a trend, it needs to be able to kind of shift warmer or colder with global mean temperature. So I will talk about this in more detail later, but you can also use the same approach for some types of climate model simulations. So climate model simulations, which the transient ones, so that means that they change through time. They have a time series, say from 1900 to present, or whatever, like the observations do. So for example, the CMIP5 or 6 historical simulations, or the Cordex historical simulations, and the future scenarios as well count as transient simulations. Okay, so I'll talk a little bit about circulation analogues. So this is quite useful for the conditional attribution, and it involves picking days. Basically, you look at the circulation state that happened in conjunction with your extreme event, and then you pick days with similar circulation states and look at the temperature associated with them. And I'll just go through the pictures because it's probably easier to explain like that. So, for example, say this is a heat wave that happened over Southern Europe. So you would look at the atmospheric circulation pattern that was associated with this. So in this case, it's high pressure over Southern Europe. And then you would look for days with similar atmospheric circulation patterns. So all these days have similar circulation patterns. And then you would record the temperature that was associated with these days. And then you can use that to do things like see how the temperatures on these analog days differ with or without anthropogenic forcing, or between two different periods. So you have the same circulation, but you might have different temperatures between the two periods. And here's an example of this used in practice. So there was a cold winter in 2010 in Northern Europe, and this was associated with a very negative North Atlantic oscillation pattern. And so the question was, how cold would this winter have been in the past with the same circulation pattern? So you can use this analog approach to select other winters with similar circulation patterns and look at how the temperature changed relative to the past. So this is what really happened in 2010. So this is actually expressed in standard deviations rather than in degrees, but blue means it was cold. And in the analogs from the past, it was actually colder. And here's the difference between the two. So it's showing that given the same circulation pattern in the past, this winter would have been colder. And you can also look at trends in the circulation itself. For example, the number of good analogs to tell you how the circulation is changing or whether it's changing. Okay, so I think I have about 2 more slides in the first half. So this one is about different types of events. So some events are easier to attribute than others. So this graph here is taken from the NAS report, and it shows basically on this axis is the confidence in capabilities of attributing a certain type of event, and on this axis it's looking at how good our understanding of how climate change affects this kind of event. So all the events are on this side of the diagonal, which because basically we can't be more confident at attributing them than we are at understanding how climate change should affect them. And where exactly they're located depends on things like how good climate models are at simulating this kind of event, how good the observations of this kind of event are, and also how well we understand the physical mechanisms that lead to changes in extremes as a result of climate change. So heat waves and cold waves are the easiest events to attribute because we have good observations, because the climate models simulate them well, and we understand why climate change should affect them. Whereas some other events are more complicated. So wildfires are particularly complicated because you can't simulate them in a climate model, and they're not just caused by climate, they're also affected by land management choices and whether or not somebody accidentally lights a fire. And but you can look at things like fire weather indices, which combine information about temperature and amount of precipitation and wind and things like that, but they're fairly complex indices. So wildfire is quite low on the level of understanding. Severe convective storms or things like tornadoes are too small to simulate in climate models, and also because they're small, it's kind of easy to miss them also in observational data sets. We look at something in the middle, extreme rainfall is also hard to simulate in a climate model if it's convective rainfall. And for that, you need convection permitting resolution. But we do have an understanding of how climate change should affect this kind of event because the water vapor increases in a warmer atmosphere. So that means there's more moisture that you can rain out as extreme precipitation. So we expect these events to be increasing in magnitude. Let me think, what else do I want to say? Things like tropical cyclones are also a bit difficult to simulate in climate models, although we can simulate them, just maybe not perfectly. And also the understanding of how they should change with climate change is also not totally clear. I think there's evidence that the strongest tropical cyclones should become more intense, but how overall numbers should change and all that is not totally clear. And then I'll just say something about droughts as well. So droughts are complicated things, and there's many different ways you can look at them. So you can just look at a precipitation deficit, or you can also take into account evaporation or even soil moisture, or you can even look at water availability in rivers and lakes and groundwater. And so obviously as this gets more complicated then, so it gets more complicated to look at the drought too. No, I'm just thinking if there's anything else I wanted to say about droughts. I mean, some components are easier to understand than others, like temperature increase would cause more evaporation. And then there's also precipitation changes. And I was also going to say that observations of soil moisture are pretty bad, and I think it's also not that great in climate models, so that doesn't help. Okay, and then here's the last slide of the first half. So I just wanted to say something about rapid operational event attribution. So this is where you attribute an event within days or weeks of it happening. So after an extreme event, there tends to be a lot of questions about the role of climate change in it. And so in order to respond quickly to these questions, which, for example, could be asked by the media, some groups are trying to do this rapid attribution. The World Weather Attribution Group is kind of an important one for doing this. And so they have to use tried and tested approaches in order to get a fast result. So they actually have a website. I've put the address here. It's worth checking it out. They have some examples. For example, they have the flooding that happened in Germany this summer. They also have the heat waves that occurred in Western North America earlier this year, and lots of other examples. So that can be quite interesting. So I don't know what time it is. Should we have just like a quick break, like 5 or 10 minutes, and then I'll go on to the second half?
Yes, we can have a short break, maybe 5 minutes to make some coffee, and then we can come back.
Okay, yeah, sounds good.
So 10 to 10, we'll be back.
Okay.
See you soon.
See you.
Question, because but I just need to think about it a little bit. I'll put something in the chat.
Okay. Any other questions?
It seems that we have no more questions.
Okay, let's carry on then. Always takes me a few seconds to figure out how to share my screen again. Okay, so hopefully you see it.
Yes.
Good. Okay, so part 2 is looking at the main steps in carrying out an attribution analysis following the world weather attribution approach. So that was what I was talking about on the previous slide. So rapid operational event attribution. So a lot of this material comes from this Pathways and Pitfalls in Extreme Event Attribution paper. This is on your reading list, it's in the shared folder, so that's what it looks like. So there's about 8 different stages in doing a rapid attribution analysis, and I'll go through them. So the first is analysis trigger, which is when you decide whether or not to do an analysis. There's also, you have to define the event. There's an observational trend analysis, climate model evaluation, climate model analysis, and then the hazard synthesis is where you bring all the results together in an attribution statement. Just realized I don't have my laser pointer. Okay, now I do. And then putting it into the context of trends in vulnerability and exposure, and then communicating the results. So we start with the trigger, so that's which events to analyze. So there are too many extreme events happening in the world to analyze all of them as a rapid operational event attribution analysis. So you need some kind of criteria for deciding which events to analyze. So this could be, for example, impact related criteria. So for example, the number of deaths or people affected, or economic damage, and that could be in absolute or relative terms to avoid just picking rich countries, for example, with the economic damage. And for the World Weather Attribution group, often they analyze events which the Red Cross and Red Crescent societies launch an appeal for. It could also be demand driven. So if a lot of people are asking about it, there's lots of public discussion, or the media or stakeholders are asking about the causes of an extreme event, then that can be another reason to analyze it. Or it could be a record-breaking event or a near record-breaking event, which makes it interesting. There's also practical considerations of whether it can be done within the given time frame, whether there's enough manpower to do it, whether there are climate model simulations available to do it, and observations. It's helpful to also have local expertise in informing about observations and other things. And it needs to be an event that climate models can represent. So you couldn't attribute a tornado, for example, because we can't simulate it. So far, in event attribution studies more generally, so not just the WWA, but more broadly, there is a bias in the events chosen so far. So the geographical coverage is not even, as we saw before. It tends to be affected by where the researchers are who are conducting the analysis, which events are interesting to them. There's also a bias towards events which we expect to be affected by climate change. And events that are getting rarer, for example, cold waves, tend to be underrepresented just by the fact that if we wait until a cold wave happens to analyze it, well, if they're getting rarer, then there are less of them. And in contrast, heat waves, there are more of them. So cold waves end up being kind of underrepresented. And so this prevents synthesis across studies. Okay, so then the second step, once you've decided that you're going ahead, is the event definition. And so the results can be sensitive to the event definition, so it has to be documented well and communicated well. So in practice, this involves choosing the spatial and temporal definition of the event. So there are different approaches to choosing this. So one approach is to maximize the signal to noise ratio. So a large area and a longer temporal scale tends to give a better signal to noise ratio, but then it tends to be less impact relevant. So an example of this is the first event attribution study by Peter Stott on the 2003 heatwave that we saw before. So this was actually done over quite a large area. It was maybe all of southern half of Europe, and it was for the whole summer, whereas actually the heatwave was more kind of smaller than that and didn't last as long as that. So this definition was not quite so impact relevant, although it did allow a clear result. Another way to approach it is minimizing the probability of the event. So you select the event in such a way that it's the rarest, or you can maximize the impact relevance of the definition of the event. So this is what WWA do, so try to select the event in such a way that it's kind of related to the impacts that happened. And in practice, some of these approaches actually overlap. So you have to choose things like the time scale. Are you looking at a one-day event, multiple days, a month, a whole season? Are you looking at a station, a city, a region, a country, or larger? Are you maybe for flooding or extreme precipitation, maybe you would look at a river basin scale. So in practice, definitions can include things like 1 or 3 day average maximum temperature, which we can call TXX or TX3X. So the annual maximum 1 day temperature can be particularly relevant for impacts on outdoor laborers, for example, whereas the 3 day maximum temperature tends to be more relevant in Europe, where people spend quite a lot of time inside. Or another example could be something like 3 day precipitation over a river basin. And you have to choose what variable you're looking at. So for temperature, you could obviously look at temperature. That's the most straightforward way of looking at it. But you could also look at heat stress indices. So these combine temperature and humidity and are supposed to be more relevant for impacts on human health. For flooding, you have a number of choices. You could look at precipitation averaged over a basin as kind of a proxy of flooding, or you could use a hydrological model. But flooding is complicated because there are lots of factors that play into it. For example, drainage basin management. If you have a lot of impermeable surfaces, for example, or if you have flood defenses or not, and that kind of thing, if there are reservoirs or dams, or whether the soil was already wet when it started raining, and all that kind of thing. So it can get a bit complicated, and sometimes it's easier just to look at the precipitation aspect. For drought, as I said before, there's lots of different definitions, so you have to decide which ones to use, and generally precip only is the easiest, and then it gets more complicated as you go along. But whatever we choose, it has to be something that we have observational data for and that climate models are able to simulate. And then you also have to think about the framing. So it tends to be a class-based framing. So all events of the same size or larger than the one that happened. And you have to decide whether it's going to be a conditional attribution or unconditional. So do you want to only select events with the same phase of ENSO as what really happened? That would only be relevant in places where ENSO is important and for events where ENSO would be expected to contribute. Or are you only interested in events with similar atmospheric circulation patterns? Or are you interested in all events, and do you want an overall probability? Okay, working out what actually happened during the event is not always as easy as you might expect, especially straight after an event when the data hasn't always been released straight away. So this is an example. I forgot to say that when I haven't said where the plots come from, they come from the Pathways and Pitfalls article. So this one comes from that article. So this is about Hurricane Harvey in Texas in 2017. It's looking at the maximum 3-day precipitation. And so there's 4 different observational data sets. This one is a station-based data set. This one is also station-based, but it's gridded. This is a radar, and this is a satellite, and you can see that they're all quite different. And so the radar should be the most accurate, but it only has data going back to 2005, which is not long enough to do an event attribution study with. So in practice, they chose to do it with 2 data sets, these 2. Okay, which brings me on to the observation-based analysis. So there are certain data requirements. You need a long time series, at least from 1950 or preferably longer. It has to include the event in question. It should be as homogeneous as possible and not influenced by other factors like station changes or urbanization. It helps having a local expert who can tell you about which data is the most reliable. And you can also, of course, repeat your results with more than one data set. So the purpose of looking at the observations is...
You hear me?
Yes.
I have to ask.
Here we are. Okay. Let me see.
Može na chat, može da se kopira, sada smo podesili da može copy paste se chat.
Okay, these are graphs from the first observed probability and trends. Are they okay?
Sorry, I can't actually hear you that well. I know I said I could, but I think the microphone, your microphone is muted and a different microphone is on.
Yes, yes, okay, now we hear you, Carley.
Oh, you hear me, but I can't hear Dragana very well.
Dragana, you cannot. Okay, let's try now. Probably, Dragana.
Can you hear me now?
Well, I can hear you through a microphone that isn't your microphone. I hear it through a different microphone.
Probaj tvoj, uspijevaš? Sad ću ja.
Možda možeš kod mene doći. Ovdje doći, Dragan. Evo ovdje kod nas. Ovdje se pa objasnim. Evo tu. Ja ću ti vrtiti ovo rešite.
Da, ovo je sad moj screen. Ovo 3D ovaj. You hear me now, okay?
Yeah, now it's good.
Nice, okay. Dole. Yes, this. Okay, this is the first graph that we did. Is it correct?
Yes, it looks correct. So that's just the raw time series of daily maximum temperature from the station data. So before we've done anything to it, we just looked at it just to make sure that nothing strange was happening. So we're just looking for inhomogeneities or, you know, weird jumps in the data or missing data or something like that. So to me, that looks okay. And then we have the seasonal cycle underneath. So that can be useful to compare to the climate model seasonal cycle. I think actually we don't do that in this practical, but you could do that. And that's particularly relevant if you were looking at precipitation. Sometimes the climate models might have the heaviest rainfall at the wrong time of year, perhaps. So that's something to look out for. But I think for temperature generally, it's probably okay.
Okay. Then the next one. Profesor, možete scroll. Ne znam što dešava.
Okay, so that was the same thing as the first time series, but it's plotted as anomalies.
Yes.
So,
Those are daily anomalies, Carley.
Yeah, I think so. Yeah, so I didn't really look at this one too closely, but looks okay. And then the next one is looking at fraction of missing data. Oh, not that one, but the previous one.
The previous,
Okay, some missing data, yes.
Yeah, so there's a bit of missing data in the last couple of years. But otherwise, there's not really much missing data, so that's good.
Yeah.
Okay.
Yeah, okay. Okay, so this was showing the time series of the days leading up to the
Sorry.
it's all right. Leading up to the heat wave and the days afterwards. So you can see that red thing in the middle, that's the heat wave. So you see it was actually longer than 3 days. So we could have used a definition of maybe longer than 3 days. But we'll just stick with 3 days just for simplicity in this case, because it just makes it easier in terms of the data and how it's stored on Climate Explorer and what's already processed on Climate Explorer.
Carley, may I ask a question, please?
Yes.
This black line that divides the red areas and blue areas, this is the climatology. This is the mean between 1950 or 2020 or 81 2010.
So it seems to be 91 to 2020, just from the title. I mean, I didn't know which period it was using,
Okay.
but the title, yeah.
These
We may
are
not.
actually the days above the threshold defined for the reference period.
Yes.
Okay.
Well, yeah. So it's showing the well, it's showing how hot it is, but then you have the reference period, so you can see if you're above or if you're below.
Yeah. Thank you.
Okay.
Okay. Was there more?
Yes.
This is
The
3 day
3-day mean
running
temperature.
average.
Yeah. So this is actually it's the 3-day maximum temperature of the year. So it's calculated. You have daily maximum temperature, and then you do a 3-day running mean, and then you pick the maximum of each year. So it's the hottest 3 days of the year. So if you can scroll back down to it again.
Još dole, još.
Yes.
To, bravo.
Okay, thank you. So I mean, do you notice anything about this time series? Like, does it look to you as you would expect?
We have almost the same values in 1950 and in the 2000s.
Yeah, that's true. So yes, it has a downward trend, and then it has a upward
first
trend.
Downward and then the upward trend.
Yeah, so I think if we were doing this for real, we'd probably want to understand more why it has a downward trend at the beginning, because it's maybe a little unexpected. So one thing that I did when I was looking at this is I also had a look at the Belgrade station to see if it shows the same thing, and it does actually. So it's not this specific station, like it's not a problem just with the station. It seems like this really happened. So there could be a number of causes. It could be something like aerosols, for example. I think, yeah, so anthropogenic aerosols, they have a net cooling effect, and I think possibly the timescales of these trends kind of fits with when the aerosols were increasing and then when we cleaned up the air, sort of thing. So that's one possibility, or it could be decadal variability. So we don't really know what it's from, but we will just proceed anyway. And so it might be that it confuses our results a bit. We might not get a stronger sort of signal as we might have done if we didn't have this downward trend at the beginning. So I think the second one is more or less the same.
Yeah, it's just
thing.
an anomaly.
Yeah, just expressed as anomalies. And then I don't remember if there was anything else.
Yeah, we had a
Yes,
running mean, running standard deviation.
Oh yeah. Yeah, so the idea is to check whether the variability changes a lot over the time series. So in our case, it kind of starts off a bit bigger, then it becomes smaller, and then it becomes bigger again. So I'm not totally sure what to make of the graph in terms of how much it can change with it still being okay, but from what I can gather, you're supposed to compare how big the changes in the red line are with the width of the confidence interval. And so if you have a really obvious trend and the confidence intervals are quite narrow, then it would indicate that the variability was changing through time. I think in our case, it's probably okay. Yeah, I'm not 100% sure about that. But let's just assume it is okay.
I'm just summing up in Serbian.
Okay, yeah.
Standardna devijacija stvari pokazuje varijabilnost klime unutar istraženog perioda. Koliko je odstupanje od te srednje vrednosti. Što su veći skokovi u standardnoj devijaciji, to će veća varijabilnost biti. To je ono, ako se sećate što je Manfred pričao o onim njegovim residuals. To je ono što ne može da se objasni, znači sa običnom formulom, sa običnim onim ta variabilnost i ovo nam u stvari to pokazuje tako. This standard deviation, the running mean of the standard deviation actually tells us the variability of maximum daily temperatures in Novi Sad. And if the standard deviation is actually having higher jumps and higher lows, the variability of climate, of maximum temperature was higher at that period. Am I right?
Yeah, so yes, it's looking at how much the annual maximum temperature varies through time with a 15-year running mean.
Also, I have another question. Why did we use 15-year running mean? Because we were taught that for a climatological cycle, we have to have at least 30 years of data.
Yeah, that's a good question. I used it because that was what was in the instructions originally.
So we can also try to 30-year running standard deviations to see how it changes through climatological cycles of them. Okay, okay, I understand now. Yes, thank you.
Okay, yeah, you can try it with the 30-year mean.
Okay.
Yes.
We are now at the step 3.8, and it is about extremes, fitting the probability distribution of extremes. Should we go ahead and try it ourselves?
Yeah, I can just say a few words about it first. Let me just share my screen. I have too many things open. Hang on. Let me just find myself. Okay, so yeah, we fit in this step. We're going to fit the GEV distribution, and we'll use the smoothed global mean surface temperature as a covariate. Do you see my mouse, by the way?
We can see, yeah.
Yes, yes.
Okay, that's good. Yeah, so we'll select a GEV because we're looking at block maxima, so that's yearly maximum in our case. And the constrained shape to 0.4 GEV, that's like a technical detail, but I think it's just to stop it doing something crazy. So yes, the distribution shifts with global mean surface temperature, and for the global mean surface temperature, it's basically pre-calculated in Climate Explorer, and it's based on a observational data set, and it's smoothed, like with 4-year smoothing, to try and get rid of variability associated with ENSO. So you can do this, and then you'll end up with this table, which is a bit confusing looking. So when you have the table, I will explain what the table is showing, and it will also produce some graphs as well, so we can talk about those. So yeah, it probably won't take you very long.
Okay, so we'll now try to fit the distribution.
Yeah.
We managed to do the distributions
Okay.
and to make the plots, but we are not very sure how to understand the plots. So can somebody please share the screen and come here to explain what we did? Because
I mean, for talking about the table, it might actually be easier if I share my screen, because then I can point at things.
Okay.
Okay.
That's a good idea. Sad ću naširuje svoj, pa će nam objasniti šta znači.
So just a second. I have 2 screens, so I'm sometimes struggling a bit to get things in the right place. Oh no, what have I done? No, it's okay. Okay, so you see something different to what I do.
We just see the Word document.
Yeah, but I can see what's on your screen, and it's not the same as what's on mine. Okay, now it is. Okay, so yeah, this table that comes out looks a bit complicated at first sight. Just want to zoom in a bit, a second. Oops, that's not how to do it.
Kako je ovo ne vidite? Ne se nešto smanji. Pa vidi koliko je ovo. Vidiš koliko je smiješno. Kako to?
Okay, so so I'll try to go through what everything is in this table. So first you have, it says covariates and then 1900, 2007. Just a second. Can I annotate? Interesting. Or spotlight. Okay. So this is basically how the global mean surface temperature is changing between the two periods, and it's expressed as anomalies relative to some period. That's why you have minus something and then 0.6. Do you see that the global mean surface temperature has warmed between 1900 and 2007? This is the number of years that we used in our analysis. So we have 71 years. And then this is the equation of the GEV. And then we have, these are the parameters of the GEV distribution. So we have so mu, that's the location parameter, and then sigma is the scale parameter. And then this one is the shape parameter. So these will be useful when we when we repeat this for the climate model. We will want to compare whether these values are compatible between the observations in the model. So we will look at, so these are actually the confidence intervals, so the 5 to 95% confidence intervals. So we will look at whether these intervals overlap between the model and the observations in the validation step. And then the interesting parts. So here we have the return period for the 2007 event. So it's a 1 in 20.5 year event, 20.45. And here is the value associated with that. So in 2007, it was 38.7 degrees. And then in 1900, the comparison, the return period was about 42. So the probability has doubled. And actually here we have the probability as its own entry and the probability ratio. So this is the most interesting number in this table, is the probability ratio. So we see that the likelihood is increased by 2, twice as likely. And then we also have a change in intensity. So it's 1 degree or 1.1 degrees hotter than the heat wave would have been if it had happened in 1900. So did that make sense, or do you have any questions about the table?
No, do you understand the table? Stavite svi razumeli. Ako niste, kažete šta nije jasno. In general, we understand the table. Actually, as you said, these return period events for 1900s is 42 years. So during 1900s, every 42 years, we would have an event like the one that happened in 2007.
Yeah.
But now in 2007, we have a return period of 20.5 years, which means that every 20.5 years we will have some severe events like that one.
Yes.
Okay, so we actually understand the table. Yeah.
Okay, good. So then we can move on to the graph.
Mm-hmm.
So this graph is showing the relationship between the global mean surface temperature and the index that we're looking at, so TX3X.
Mm-hmm.
So we use this to work out how much to shift the GEV with time or with warming. And then this one is, so this is return period plots. So the red one is for 2007 and the blue one is for 1900, and essentially they're the same thing. It's just the blue one is shifted down by about 1 degree And then you can use this to read off the return period. So you can read across on the purple line, that's the magnitude of the event that we observed. And then when it crosses with the other lines, you read down. So it was a 1 in 20 year event, and it used to be a 1 in, well, we already know it was a 1 in 40 year event. It's slightly difficult to read this scale. And the confidence intervals, I can maybe say something about those. So you'll notice that we have these confidence intervals, and the way that those are calculated is through a bootstrapping technique. So Manfred, I think he mentioned bootstrapping in the last workshop, but it's where you resample your data thousands of times. So basically, if I have 71 years of data, in this case, I take a random sample of 71 years of data, but I can replace the years after I took them. So maybe I take the same year more than once. So each time I take 71 random years, and I kind of effectively calculate this return period curve, I suppose, and then I just keep doing it 1,000 times, and that gives me a range of results that I could get. And it's supposed to show some of the uncertainty and the fit of the GEV. So yeah, do you have any questions about anything?
Actually, I have. I always have questions. Those
Okay.
red and this on the next, yes, and then the next picture figure, we have red crosses and blue stars. Those are actually values from the time series.
Yes.
Okay.
Yes.
So we actually derive the return periods where the blue and the red line crosses the purple line. So
yes.
Okay, thank you.
Okay. Yeah, you're right.
Okay. So
Okay, so we can, I also suggested in the instructions that you can, instead of putting 1900 in the box, you can put 2021 in order to see how the probability of the heat wave has changed between 2007 and 2021.
okay.
So you can do that and you'll get some results, and then we can talk about what it shows.
Okay.
Okay, so you see the table?
Yeah.
So the important bits from this table are the probability ratio and the change in intensity. So the probability ratio, so it's 0.75. That's actually I mean, it's a less than 1 means a decrease, but that's only because we're looking the way around we're looking at it. So it just means that in 2007, the probability of this event